the 21st lecture, and we continue our discussion on differential amplifiers. To recall the differential amplifier, this is the circuit. And we calculated the DC quantities. We assumed VB1 minus VB2 as equal to VD, VB1 minus VB2 equal to VD, and we found out an expression for VOD in terms of VD through the transistor junction relationships, that is I sub C equal to I sub S exponential VBE by VT, V subscript capital T. In the process we found out that the two currents IC1 and IC2 vary exponentially like this, that is when one is negligible the other is almost full, and therefore there is a possibility of switching from one state to another, and I commented that this forms the basis of utilization of the EC emitter coupled pair ECP in ECL, that is emitter coupled logic. From the two current variations we then went to the voltage variations, that is VC1 and VC2, and we showed that VC1 and VC2 vary in this manner. The same type of variation because they are linearly related to I sub C1 and I sub C2, and VOD which is this curve is the difference between the two. VOD is equal to VC1 minus VC2, and we showed that when the range of VD by VT is between -2 and +2, the variation is approximately linear, and this is the range of operation, range of interest to us in the analog electronics course, because we want linear amplification. And I also left some algebraic steps to you to show by substituting the expressions for I sub C1 and I sub C2 that the voltage VOD is given by this relationship minus IEERC tan hyperbolic VD by 2 VT. I will write this expression again, and this is where we start from today. VOD, the differential voltage, is equal to minus IEE RC, and you remember why minus comes, because it is IC2 minus IC1 times RC. IEE RC tan hyperbolic VD by 2 VT. Was there any problem in deriving this relationship? Was there a problem, or you didn't derive? Please do. If there is a problem, let me know. Now the variation of VOD versus VD by VT is approximately linear, as I had told you. Approximately linear, and these values are, one is I sub EE R sub C, and the lower value is minus I sub EE R sub C. Now comes the utility of the DC analysis. You see, if I change VD a little bit, VD changes to, let's say, VD plus delta VD, then delta VD is the perturbation on the Q point, on the operating point, and therefore this corresponds to a signal. All right, this corresponds to a signal capital V sub capital D. Under this condition, VOD naturally shall change from VOD to delta VOD, and this appears in response to an incremental change in the input voltage of VD, and therefore this is capital V subscript small o subscript small d. This is the output signal, and the ratio of these two, VOD by VD, shall give you the gain of the amplifier. All right, this is the advantage, this is the utility of the DC analysis, and it also, the DC analysis incidentally also showed what range you should be concerned with for linear amplification. Okay, now therefore the gain of the amplifier, which is AD, the differential gain, would be equal to dVOD, I beg your pardon, it would be A sub D would be dVOD, that is a small change in the DC output due to a small change in the DC input. Okay, this slope, this ratio shall give you the gain. You recall that this is the output signal and this is the input signal V sub D. Okay, and therefore if we differentiate this relationship, I should be able to get a gain. That is, if I differentiate VOD with respect to VD, what do I get? I get I sub EE minus RC, tan hyperbolic differentiation gives sec hyperbolic squared. Okay, sec hyperbolic squared or VD by 2 VT, and then this has to be differentiated with respect to VD, so 2 VT shall come here. Agreed? This shall be the gain. Now you notice that the gain is a function of the Q point. The gain is a function of where your VD is, that is the DC value, VBE1 minus VBE2 or VB1 minus VB2. However, since the curve is approximately linear in this range, since the curve is approximately linear, we can simplify the gain calculation by taking VD equal to 0. That is, obviously the curve will be maximally linear at this point. As we go out from 0, either on this side or this side, the curve starts bending, and therefore we find the gain at VD equal to 0. If I put VD equal to 0, sec hyperbolic is unity, sec hyperbolic of 0 is unity, and therefore A sub D becomes simply equal to minus IEE R sub C divided by twice VT. This is the gain, and the gain has been derived not from the AC equivalent circuit, it has been derived from simply DC calculations, and our purpose was to establish not only the gain but also the range of operation, that is, what is the dynamic range permitted for the input. If we exceed twice VT, about 50 millivolt, then we shall not get linear amplification. So the input signal swing must be limited to minus 2 VT to plus 2 VT. That is a total peak to peak swing of 4 times VT, approximately 100 millivolt. That's it. And this is true for approximately all BJT amplifiers at room temperature. What happens with FET we shall see later. But this expression also is very illuminating, minus I sub EE R sub C divided by twice VT. If you recall the circuit of a differential amplifier, I sub EE is IE1 plus IE2, the two emitter currents, and since beta was assumed to be very large, the emitter currents are approximately equal to the collector currents, therefore this is twice I sub C, IC1 and IC2, they are identically biased, so there is no reason why the current should be different. And if I substitute this, then I get AD equal to minus I sub C R sub C divided by VT. And you also remember what is IC by VT? GM. So it is minus GMRC, which is a very familiar expression. This is the gain of a simple common emitter amplifier with a load of R sub C. If the load is different, if there is another load capacitively coupled, there is no capacitive coupling here. So this is the load, and therefore by using two transistors in this emitter coupling mode, we haven't gained much in terms of gain. Is that correct? The gain is still minus GMRC. I could have obtained this with a single BJT instead of two. What is it that we have gained? We have not gained in terms of gain. We must have gained somewhere else. What we have gained is the following fact, that VOD equal to 0 when VD equal to 0. What does this mean? It means that when there is no signal, there is no voltage difference between the two collectors, which means that the DC offset is 0. DC offset is 0. That means if the two bases are at identical voltages, the two collectors shall be at identical voltages, and these collectors now, if you recall, these are our output points, and there is no reason why these two cannot be applied to the next stage of the differential amplifier. That is, I have next stage of the differential amplifier without any DC offset. That is, this will not create a signal at the input of the differential amplifier. Is that clear? The input to the next differential amplifier will arise only when there is a signal. When there is no signal, there will be no DC offset here. In other words, VOD shall be equal to 0. This is the major advantage. Okay, and we can couple, we can cascade a number of them to get any gain that we want. On the other hand, if we have a single stage common emitter amplifier and we want to increase the gain by using cascading, we require capacitive coupling. Otherwise, the DC will affect the next stage. All right. Obviously, you cannot, VCE cannot be connected directly to the base because the next transistor will then be saturated. Is the point clear?
So we also have noiseless amplification in this case.
We have, yes, we have the signal to noise ratio S by N at output will be much greater than signal to noise ratio at input. I am coming to this advantage a little later when I calculate the CMRR, common mode rejection ratio. Okay, now we go to the AC analysis. All right. Let us see. DC analysis has given us gain, has given us the range of operation. Let us see what AC analysis gives. Now in AC analysis, we first make analysis for differential mode. For a differential mode, what you will apply is a differential voltage V sub D. This is the AC quantity now, capital V subscript small d, AC quantity, and we are taking the RMS values. What we do is we apply a differential signal between the two. Now, since the two transistors are identical, operated under identical conditions, I can look upon this as if I had applied a VD by 2 here from the base to the ground, and another VD by 2 here from the base to ground, but with a reversed polarity, that is plus here and minus here. Is that clear? this facilitates the analysis. This facilitates the analysis. So this is what I shall use, that is, we apply a differential voltage between the two bases and we look upon this as if equal and opposite voltages are applied to the two bases. This is what will be done in practice. In fact, one of them will be grounded and the voltage will be applied here. What counts for the differential amplifier is the difference voltage at the input, not the absolute voltage. So if this is at 0, then this is at Vd. If this is at minus Vd by 2, then this is at plus Vd by 2, so that the difference is still Vd. Okay, let's look at the equivalent circuit. If I do that, then let me view the signal also. Instead of Vs, let me view this as Vs by 2 with this polarity and Vs by 2 with this polarity, plus minus. Okay, so that the total voltage applied is Vs, the difference voltage. Now Vd will be created by Vs by 2 in series with an Rs. They are identically. It is only for the purpose of analysis. We in the actual design we will apply the signal only at one terminal. Okay, we may apply to two terminals also, but one terminal suffices. So this voltage is Vd by 2 and this voltage is Vd by 2 in the opposite polarity, plus minus. This is my base 1 and this is my base 2. From base 1, if you look at the equivalent circuit, we have an R pi 1, base 1 to emitter is R pi 1 and base 2 to emitter is R pi 2, and the two voltages there are V pi 1 and V pi 2. I will run short of space V pi 2. Okay, then the two emitters are connected together. This is E1, E2, E1 and this is E2. They are connected together, and from this common point we get an REE. As far as AC is concerned, VEE is ground. Okay. Now in the collector circuit, we have a GM V pi 1, this is collector C1, and there is a collector C2. We are ignoring everything else. GM V pi 2, if you wish you can say GM1, GM2, but they are identical because I sub C's are identical. GM V pi 2 and then what do we have? From collector to VCC there is a resistance of R sub C, and from collector 2 to VCC there is another resistance R sub C, and these two are connected to ground. You notice that we have ignored R0, isn't it right? Small R0. It should have come in parallel with C1 and C2, R01 and R02. Both would be identical because the collector currents are identical, the early voltages will be identical because they are made on the same chip. However, as you shall see later, although we had ignored it, it could be taken into account by a very small trick. And that trick, before I explain this trick, let's notice that the current that flows here, the current, AC current that flows here, let's call this I. What should I have the symbol? Small e 1. The current that goes here must be equal and opposite to the current that comes here, because the two signals are equal and opposite, and therefore IE2 would be equal to minus IE1. IE2 would be equal to minus IE1 because of symmetry and because of anti-polarity excitation. And therefore, what virtually happens is IE1 comes here and goes away like this. Okay? IE1 comes here and goes away like this. No current flows through REE, which means that this point is virtually grounded. This point is grounded. And if that is so, then the equivalent circuit simplifies greatly.
So should this point be open circuit?
Which one?
This point at which you are grounded very early.
The potential is 0 because
There's no current.
But
flow.
there is a ground in the ground. Current would go through the ground. So
okay, just a minute. This point,
yes.
no current flows to RE. So what is the potential of this point? 0.
Yes,
So it's virtually grounded.
But sir, if it is
Sir, it's not necessarily 0, sir.
Why not? Where would a current source come? AC signal here is 0. AC voltage here is 0. Because no AC flows through RE. And therefore the potential is 0.
So then Vs by 2 is equal to V pi.
Vs by 2 is equal to?
V pi.
Yeah,
Sure.
That's right. Vd by 2 would be equal to V pi 1. Quite
V by
correct.
2.
Quite correct. Vd by 2 would be equal to V pi 1. Vd by 2 here would be minus V pi 2.
Sir,
Yes.
so do we need an RS there?
Do you need an RS there? Yes.
So because we are applying signal at only one base and you said the other base is grounded.
This is the way of looking into a single voltage applied between the two bases. As I said, I decompose this signal voltage into two voltages.
So that means the resistance of the signal voltage.
This is
also-
only a conceptual simplicity. We assume that identical sources with identical source resistances are
That
connected.
means the resistance of the source also you are decomposing.
That's right. When you bring the source, you must bring its resistance also. But we have broken up the voltage into two parts, Vs by 2 and minus Vs by 2. Okay? Now, if this point is grounded, then you notice two very interesting things. That R01 was to come in parallel with GM V pi 1, and R01 can therefore now be combined with RC. Is that clear? And therefore there is no problem, you can combine RC with R01. And therefore in the hybrid pi equivalent circuit, all that we are retaining is R pi, R0 and GM, nothing else. Rx and R mu are being ignored. Of course this is mid-band equivalent circuit. At high frequencies things will be different. Okay? And there is no low frequency cutoff because the amplifier is direct coupled. It's not coupled through a capacitance. Okay. Now we can calculate the gain very simply. I can, because of this ground, I can only consider half of the circuit. And this is called the half symmetry analysis. So what we do is we have an RS. We just take one of the transistors, Vs pi 2, and then we have R pi 1, which now goes to ground. This is V pi 1, which is equal to Vd by 2 with this polarity. Then we have GM1, GM V pi 1 and 2 are the same. This goes to ground, and all I have is an R sub C to ground, and I have said it could be RC parallel R01. Okay, and this is my voltage capital VOD divided by 2 with this polarity. From the collector to ground, the voltage is VOD by 2. This voltage would be VOD by 2, and this voltage would be minus VOD by 2 by symmetry. Okay, so what is the gain? A sub D is VOD by 2 divided by VD by 2, and obviously this is equal to minus GM RC. The same result that we had derived from DC analysis. Okay, the same result. We don't expect anything different. If it was different, then we would have suspected our DC analysis. But it also shows that it also shows two things, that the output is an unbalanced output. We have taken from the collector to ground. Is that clear? We have taken an unbalanced output. The input is balanced, the output is unbalanced. So it's a balanced to unbalanced transformer. Okay? And the second thing it shows, yes.
So even in R0 also.
I could take R0 also. If you desire, we call it RC prime.
So in that case, the DC analysis and AC analysis results would be different.
That is correct. Okay. If R0 is also taken into account, R0 was not taken into account in the case of DC analysis, then they are slightly different. But RC in practice is very small compared to R0. Therefore, they are, for an engineer, they are equal. Okay. The other thing that you see is, if the output is taken from here, what is the output resistance R0? It is simply equal to RC. What is the input resistance?
RS plus.
What is the input resistance? Input resistance is the resistance in here. That is not correct. Okay. This point is a virtual ground. So from here, from B1 to B2, remember the voltage is applied between the two bases. So what will the signal source see? R pi 1 plus R pi 2. This is the input resistance of a differential amplifier. It is not R pi 1. It is R pi 1 plus R pi 2. It goes like this. Okay? And the source is a single source. Sorry. So the input resistance in one stroke of pen, I can write this as twice R pi. Excuse me. I have computed the gain, I have computed the output resistance, input resistance. Now let's look at the common mode gain.
So please explain again how do we get 2 R pi?
The input the input that we apply is between the two bases. Okay? It is a different matter that one of the bases may be grounded. If it is grounded, then it is between B1 and, even if it is grounded, it is B1 and B2. From B1 to B2, the path is R pi 1 plus R pi 2.
So, but in that case, even the output is not taken in.
Output is not taken in the differential mode. No. Output is taken across one of them because we want the output to be grounded. Alright. If you want to apply to enhance the gain, then you take the output, then take the differential output and connect to the two bases of the next stage. But if this is the final stage, you take the output from one of the collectors to ground. Okay? Now, let's go to the common mode gain. In common mode, yes.
But using the DC analysis, we will consider the output as the differential output. And here we are considering it as the unbalanced output.
Right? We also split the voltage. The voltage was VD by 2 and the output was VOB by 2. So it's a factor of 2 which divides both numerator and denominator. The gain still remains the same. Okay? In common mode analysis, our circuit would be a VS and an RS. The same voltage is applied to the other base, B1 and B2. Okay, in common mode analysis, and we call this voltage as V sub C, small v sub c, and this voltage as small v sub c. The polarities shall be identical, common mode, same voltage is applied to the two bases. The differential output shall be 0, but let's see if there is an output at the collectors. Now the equivalent circuit shall go the same way. that is, we have an R pi 1 and this voltage is V pi 1, then an R pi 2, this voltage is V pi 2, it's become a bit congested, but I hope you can make it. This is V pi 2. The two emitters are connected together and connected to ground through REE. There is a GM V pi 1 here, current source. This is collector 1. There is a current source here, GM V pi 2, collector 2, and the same story, that is R sub C and R sub C. These two connect together and are connected to ground. Alright. The only thing that we have changed is the sources are identical on the two sides, and therefore the base voltages are identical, VC and VC. We want to see if there is an output from here to ground. Let's call this output as capital V O small c, VOC, output due to common mode, okay, with this polarity plus minus. Agreed? Now, because of symmetry, this current and this current shall be identical. Isn't that right? These two currents shall be identical now. It is not equal and opposite of each other as in the differential mode, which means that if this current is IE1, then this current would be IE1 plus IE2, which are identical, and therefore this will be twice IE1 or IE2. Yes.
Are these two amplifiers, two common emitter amplifiers connected cascaded to each other?
No, that's a major mistake. They are emitter coupled. When two amplifiers are cascaded together, the emitters are not common, not necessarily common. Here we have taken pains to connect another resistance here. There is a great difference. If it are two common emitters, then all these advantages would have been lost, and you had to have coupling capacitors and many other things. Signal to noise ratio would not have been improved. Now, the point that I want to mention is, as far as transistor 1 is concerned, it sees in REE twice the current that comes here, which means that the drop that it sees here is twice IE1 REE. So, as far as transistor 1 is concerned, it is as if it sees, instead of a resistance REE, it sees a resistance of twice RE. And that simplifies the circuit. If I draw the circuit once more, VS, RS, this is V, capital V subscript small, capital C. I made a mistake here. This is capital V, the signal quantity, RMS quantity, subscript is small c, V sub c, then we have an R pi 1, V pi 1, and instead of REE we have twice RE. Then we have GM V pi 1 coming here, and I have R sub C, the collector resistance, and this voltage is VOC plus minus. If you recall, we have analyzed this circuit earlier. This is the common emitter circuit with unbypassed emitter resistance, and therefore we did not repeat the analysis. We can write the gain very simply. A sub C, the gain, common mode gain, which is the ratio of VOC to VC. Same way we had taken earlier also, VOD by 2 divided by VD by 2. The output voltage divided by the input voltage is given by minus GMRC. We did this earlier, and if you desire you can carry this out again. It would be 1 plus twice REE beta plus 1 divided by R pi. This is the gain. And if beta is much greater than 1, as has been assumed earlier, this is simply beta by R pi and therefore GM, and therefore this is approximately equal to minus GMRC divided by 1 plus twice GM REE, and usually twice GM REE is much greater than 1, so the gain is simply minus RC divided by twice REE, in consonance with what we had found earlier, that if there is an unbypassed emitter resistance, the gain is controlled by the collector resistance and the emitter resistance. It's simply the ratio of the two. Okay. Now let's keep it like this. But one thing is also obvious, that the output resistance here. What is the output resistance? It's again R sub C. Why? Because there's a current generator here. Okay. R0 is again R sub C, as in the differential mode, but there occurs a C change in Ri. What is the input resistance? R pi 1 plus beta plus 1 twice REE. So in the common mode, in the differential mode it was simply twice R pi. In the common mode, a large resistance is added to R pi. So in the common mode, the input resistance is high. All right? Yes.
So when we're calculating output resistance,
Yes.
the currents, how did you get the output resistance as RC?
Okay. If Vs is term 0, if Vs is 0, then V pi 1 is also 0?
No. So
No?
So the
It's not zero.
So some of the current may flow.
so some of the
So
current
some
will
of
flow
the
through
current will
power.
flow through it.
Okay. We did calculate this earlier, isn't it?
Yes.
GM1, GM V pi 1, 2 RE in parallel with R pi 1 and RS. Okay? All right. What is this? Is RC, V and I. The question is good. I don't know if the answer would be good. This comes to twice REE. Then what? From twice REE you have an R pi 1 plus RS, plus RS. Oh, I cannot, made a mistake. It is R pi 1 plus RS. I must show V pi 1. V pi 1 would be minus here and plus here.
So the opposite.
Minus plus.
Minus plus.
Yes, that is correct. Minus plus. Now the question is, this current, can it have a component here? Yes? Can this current flow here?
Yes.
What is the input impedance? What is the impedance of the current generator? And there is no source on the left hand side. How can you say that? Okay. I leave this to you to sort it out. How to sort it out? You assume a voltage here. This voltage, assume a voltage here, and you have to write two node equations. Okay? And find out what the result is. And let me know in the problem session. Okay? Alright. Have we calculated the input resistance? Yes, input resistance we have calculated. Now I go back to my two gains. AB is minus GMRC and AC, the common mode gain, is minus GMRC divided by 1 plus twice Gm REE. Okay. Therefore, the CMRR is a positive quantity. It is AD by AC, and this is equal to 1 plus twice Gm REE. Agreed? Which is approximately equal to twice Gm REE. What is Gm? Gm is twice IC divided by VT REE. Okay? And what is twice IC? It is equal to IEE REE divided by VT. Now, our purpose in a differential mode amplifier to make the signal to noise ratio as at output as large as possible. Is there any question on this? To make the signal to noise ratio at the output as large as possible, we wanted A sub C to be equal to 0, and we wanted A sub D to be as large as possible. In other words, we want to increase CMRR to as large a value as possible. It depends on an internal property of the transistor, that is Kt by, which is a universal constant, Vt, which you cannot change. You cannot lower this down. Vt cannot be changed. What you can change is you can change IEE. You can use a large current, or you can use a large resistance, or you can use large current as well as large resistance. In either case, in either of the two cases, the casualty becomes VEE. It has to be increased. If you increase IEE, how do you increase IEE? You increase the source voltage, that is VEE. If you increase REE, then with the same current there is a large drop across REE, and therefore you have to increase VEE. Okay? This is not permissible, this is not feasible in an integrated circuit. One of the advantages of ICs is that it can operate at low voltages. If you are going to increase the voltages to high value, not only you lose that advantage, but you also run the risk of burning the chip, because it cannot take more than a certain amount of dissipation. Very small space, heat cannot go out. Large current means large dissipation, alright, and therefore you lose that advantage. So we have to devise something to increase this factor IEE-REE, and what is done is to increase REE by an indirect means, that is replace REE, that lumped resistance, by a current source. If I can replace REE by a current source, and if the current source is an ideal current source, then REE is approximately infinity, and therefore CMRR can go to infinity, and we have an ideal differential amplifier, that is the common mode gain would be equal to 0. But since nothing in this world is ideal and transistor circuits are no exception, we will have to settle with what we get. Let us see what we can get. But before I make an analysis, let me show you how the current source is connected. Okay, let's draw the differential amplifier plus VCC. Then these two are connected together. This is where the question comes. We want to connect not REE but a current source. Okay, and then of course you have the do I have to show the base circuit? Okay, let us show. Suppose we have connected a Vs and Rs, and perhaps nothing is connected here, but truly a differential mode. Okay, we have connected a voltage here, nothing is connected, this is connected to ground, but I have connected to ground through a resistance RS. Can you guess why? Why couldn't I connect it directly to RS, directly to ground? No, that's not the.
Preserve the symmetry.
Preserve the symmetry of biasing.
Yes.
DC biasing. As far as DC is concerned, Vs is a short. Therefore, if this base is connected to RS, this base should also be connected to RS. Otherwise, there shall be a DC offset. Is that clear? And any change in DC, any change in the DC voltages between the two bases shall be interpreted by this dump amplifier as a signal. Isn't that right? Any change in this is, therefore I connect an RS here. Now the point is, I don't want to connect a resistance here, I want to connect a current source or a current mirror, and you know what a current mirror looks like. Okay, what you have is now what we have to do is two transistors. The reference transistor has to have its collector connected to the base, agreed, and these two emitters should come together if it is a simple current source. But the current that we want here, we want to control this current, and therefore we use, instead of a simple current source, what? Widlar current source. So we include a resistance here, connect these two, and this goes to either ground or to minus VEE. Okay, instead of that REE, you see the complication. We have two transistors here, and then I have to set up a reference current. How do I set this up? I have to have a resistance R here, and this resistance is to be connected to plus VCC. So this is a differential amplifier, RC. This is a differential amplifier with REE replaced by a current source. Alright, now let's look at this current source. You remember that IR, if I call this transistor as Q2 and this transistor as Q1, we had called these earlier Q1 and Q2, you call them Q3 and Q4. Okay, since we are concentrating on the current source and its effect on REE, the effective REE that is offered by Q1 and RE and a current source mode is the AC impedance looking from here, that is the output impedance of Q1 in series with RE. Okay, this is the effective REE, and you shall see that it can be increased tremendously. We have not increased VEE, we have kept VEE and VCC in the tolerable range. Effectively, we want to increase REE. If this transistor was ideal, that if its R0 was infinity, if V sub A, the early voltage, was infinite, then obviously REE would have been infinite. Okay, but since there is an R0 and VA is not infinity, therefore REE shall be a finite quantity but much larger than what we have physically connected here, RE. We shall show this. But you recall the design equations of a Widlar current source. I sub R is simply equal to VCC minus VBE2, which is 0.7 divided by R. And since these transistors are high beta transistors, I sub R is the same as IC2 is the same as IC1. Yes or no?
Yes, sir.
No. That was the purpose of including RE here, that IC1 can be made different from IC2. Okay, and they are related by an exponential relationship. What you do is VBE2 is equal to VBE1 plus IC1 RE. From that you find out the relationship between IC1 and IC2. I shall repeat this relationship.
There should be a plus VE
For me,
in IR.
plus VE. No, VBE2 from here to here is the same as VBE1 plus IC1 RE.
Same expression for IR.
IR.
Expression for IR. Okay. That's right. Plus VEE. Quite right. Okay. Now the equation that gives RE, the required value of the resistance, is the following. This is simply recalling. It is VT divided by IC1, the desired IC1, multiplied by 1 plus beta inverse, which you can replace by 1, times log of IC2 divided by IC1. Alright? For example, let's go here. I sub R equal to VCC plus VEE minus VBE2 divided by R, and RE, the resistance required, is VT divided by IC1. Let's ignore beta. IC1 log of IC2 divided by IC1, and IR is equal to IC2 because of large beta. Suppose IC1 we required is 50 microamperes. These are typical values because we want to keep the power dissipation as small as possible. Transistors usually are operated at very low currents. Suppose IC1 is 50 microampere and R is 10K. This value can be fabricated in IC technology. The highest resistance that can be fabricated is about 50K. 50 is the limit. Don't go beyond 20. You'll make the chip costlier because you'll use more resistance. But 50K is approximately the limit. If R is 10K and VCC plus VEE is 15 volt, let's say, then RE, well, then IC2 or IR becomes 15 minus 0.7 divided by 10K, which is 1.43 milliampere, and RE is, it calculates as 1.68K, which is indeed a low resistance, 1.68K. We shall show that with these values the effective REE that can be generated is of the order of a meg. Even with REE equal to 1.68K, a small resistance, VCC plus VEE, the two combined does not exceed 15 volt. The effective REE generated is of the order of a meg. Okay? Let's see how this comes about. In order to show this, obviously what we have to do is to calculate the output resistance of this transistor in the when it is operated in the current mode, in the current source mode. That is, its VBE is controlled by a reference current and a reference transistor VBE. We have to calculate the output impedance of this circuit. Let's take a simpler current source with VCC plus VE lumped into one. Alright, that will not make a difference as far as output resistance is concerned because output resistance is AC. So we take the ordinary transistor. This is connected to the base, and then we have, this is I sub C1, this is IR, This we call Q2, yes, and this is Q1. Then there is a resistance Re. Now what we have to do now is to carefully draw its equivalent circuit and calculate what impedance is offered between this point and this point.
To short the base.
Short the base? Yes. How could I draw it without shorting the base? Actually I forgot the orientation, so I had to draw this long line. So we have to draw the equivalent circuit and calculate the output resistance carefully, which task we shall do next time.